Okay, so now I'm going to talk about DFA minimization. So for a given language, there are always going to be infinitely many DFAs that recognize that language, because we can always add superfluous states. So for example, we've got the same DFA as we had before. This DFA recognizes all strings of the form 0, 1, 1, and then as many ones as you want afterwards. So, or if you prefer, 0, 1 to the n, where n is greater than or equal to 2. So here's the DFA I came up with last time. It's got 5 states. Here's another DFA that also recognizes it. All I've done is like make a separate trap state for S0, S1, S2, and S3. So it's not too hard to see that these DFAs are going to be equivalent. I've got this DFA here, which again does the same thing. All I've done is split the final state into 2 final states that just bounce back and forth reading 1s. And if ever you read a 0, you go to the trap state over here. So again, this is going to be equivalent. And this DFA here is exactly the same as the first DFA, just with these extra redundant unreachable states. Clearly, states that you can never get to are not going to be able to affect the behavior of the automata. So here I've color-coded the unreachable states in red. So it shouldn't be too hard to see that these states are not going to change the behavior, and this DFA is also going to be equivalent. Now it happens to be the case that if your DFA is minimal, that is, it's got the fewest number of states possible for that language, then it's always guaranteed to be unique. So there might be many different DFAs solving the problem, but there's only going to be one DFA with the fewest number of states solving that problem. Hopefully it's going to be this one, right? So if we want to show that a DFA is minimal, what we can do is we can run the minimization algorithm, which I'll describe in a bit. And what the minimization algorithm will do is it will identify states that are equivalent. That is, it will identify 2 states that really do, if you like, do the same thing, that they can be treated as a similar sort of state. That is, if 2 states are equivalent, then you can delete one and then change the transition function for the other, such that the behavior for the DFA, after all is said and done, is left unchanged. So this is why we care about minimization. Obviously, we want to have the minimal DFA possible. And the next video is I'll actually go through the algorithm.